Hello students, today we're going to have a review of the 4 types of conic sections that we learned about. For each type, I want to talk about what the equation should look like. I want to talk about what the geometric definition was for that shape, and then also the reflection property. So our 4 types were circles, parabolas, ellipses, and hyperbolas. And I want to talk about each one of these, and we're going to, in essence, be comparing them a little bit. So let's start by looking at the equations for each of these shapes. Now we're going to be looking at all of these conic sections centered at the origin. We will, in the next lesson, look at them when they're shifted away from the origin. But for right now, these are all centered at the origin. So for a circle centered at the origin, remember, we will have an equation in the form x squared plus y squared equals r squared. For a parabola, we have an equation in the form x squared equals 4py, or y squared equals 4px. Now I want to take a moment to compare these equations. When we have a circle, there's an x squared and a y squared term. But if there's only an x squared or only a y squared, we end up with a parabola. So this is one difference that we notice about these equations that will help us later when we're looking at more general forms of these. So after that, we have ellipses. And so if we have an ellipse, the equation is going to be x squared over a squared plus y squared over b squared equals 1, or x squared over b squared plus y squared over a squared equals 1. These are more or less the same equation. It's just we usually have a squared being the larger denominator, and so we could write it either way. But in this case, we also have an x squared and a y squared term, just like with circles. But the difference is, when we have a circle, it's just x squared and just y squared. They have the same coefficient, which is 1. For an ellipse, we will have different coefficients, because remember, a is going to be larger than b. If we had an equation like this, where a and b were the same. Let's say a and b are both 3, so we've got 3 squared, or 9, in the denominator. In that case, we just end up with a circle, because we can multiply both sides by 9 to get rid of the denominators, and then we'd have x squared plus y squared equals 9. So the difference between a circle and an ellipse is that with an ellipse, the coefficients will be different on the x squared and y squared terms, but on a circle, the coefficients are going to be the same. All right, now lastly, we have hyperbolas, and when we have a hyperbola, the equation is going to be just like that of an ellipse, but instead of a sum of 2 terms, it's going to be a difference. So we'll have x squared over a squared minus y squared over b squared equals 1, or we'll have y squared over a squared minus x squared over b squared equals 1. So the difference between the ellipses and the hyperbolas is that with an ellipse, both the x squared and y squared terms are going to be positive, whereas with a hyperbola, one of those terms is going to be negative. So by looking at the coefficients on the squared terms and whether they're both positive and whether one's positive and one's negative, or if we just have one of the variables being squared, this is going to tell us whether we have a circle, a parabola, an ellipse, or a hyperbola, and then we will be able to figure out what the graphs are going to be. In fact, a couple of lessons from now, we're going to be looking at equations that aren't exactly in any of these forms, and we'll have to decide what the graph's going to be and get the equation in the right form. Now that we've reviewed these equations, I want to talk about the geometric definitions of each of these, and I want to talk about the reflection properties. So the geometric definition of a circle, remember, is the set of all points that are the same distance away from the center. So no matter which point we have, these are all going to be the same distance. Now, with a parabola, there's also a geometric definition, and it also involves distances. But remember that we have a directrix and a focus here. And so the definition of a parabola is the set of points such that the distance from the point to the focus is the same as the distance from the point down to the directrix. And that's true with any point on the parabola. So the distance from that point to the focus is the same as the distance to the directrix. Now, I haven't drawn this perfectly, so the distances might not be exactly equal in my drawing, but that's just my failure to draw an absolute perfect parabola there. So then for ellipses, we also had a geometric definition. I'm going to try and draw a decent ellipse. That's not the worst. So remember, with an ellipse, we also have a geometric definition with the foci, and an ellipse is the set of all points such that if you take the two distances from the point to the two foci, the sum of those distances is the same even if you pick another point on the ellipse. So it's all of the points where the sums of these distances are equal to each other. So all of these shapes are defined based off of distances. There's something that they have in common, even though these are all different shapes. And then lastly, we have a hyperbola, which I'm going to try and draw not too horribly by hand. That's not the best I've ever done, but also not the worst. And we also have a geometric definition for a hyperbola, and that is the set of points such that if we look at the distances from that point to the two foci, the differences of the distances are the same. So if we were to pick another point and we were to look at those distances and we were to take the difference of those distances, the difference of these two distances will be the same as the difference of those two distances. So all of these shapes are defined as the set of points such that something is true about the distances. Now, the last thing I want to talk about is the reflective properties of each of these, because they have very interesting reflective properties. I'm going to go and try and draw all of these again over here. So we've got a circle, we've got a parabola, we've got an ellipse, not my best ellipse, and we've got a hyperbola. Really not the best hyperbola in the world, but I don't want to pause the video and rewind and make it beautiful because I don't want to give the illusion that I always draw perfect ones. So we'll deal with imperfect ones. And so each of these has a reflective property. We're going to talk about the circle last because it's not the most interesting, but I do have a little bit of a story about that. So for a parabola, remember the reflective property is that anything that comes directly into the parabola, perpendicular to the directrix, remember, gets reflected, and no matter where we're coming from, so long as we're going in perpendicular to the directrix, it is reflected directly back to the focus. So all of these get reflected in towards the focus, all to the same point. Now, if we look at an ellipse, remember we've got the two foci, anything that comes out from one of the foci will get reflected off of the end of the edge, I guess, of the ellipse, and it gets reflected into the other focus. So no matter what angle we're going from one of the foci, it gets reflected into the other. Now with a hyperbola, again, we've got the two foci, and anything that is heading towards one of the foci gets reflected off of the hyperbola and heads into the direction of the other focus. So anything that's heading in towards one focus gets reflected off into the direction of the other. And the last one is the circle, which is kind of the most basic one. Anything that starts in the center and goes towards the outside of the circle is reflected right back in towards the center, which might not seem super interesting, but I do have a story. There is a building in Boston called the Maparium, which is kind of a weird place, and it has a weird history, but there's a room in it that is perfectly spherically shaped, more or less. I mean, there's doors that open that are not spherical and whatnot, but it's a spherically shaped room, and there's a bridge in the middle, and so you can stand right in the very middle of the bridge, and if you whisper something very, very quietly, your sound waves are going to move out in every direction, and they'll be reflected back to you from every direction. So even if you just whisper a little bit, it ends up being much louder because all of the sound waves, as they move out from you and then reflect off of the spherical room, they get all reflected back to you instead of dispersing. And so whenever you speak at the very center, it becomes much louder than you had intended it to. So this is a comparison of the equations of these four shapes, the geometric definitions of these shapes based off of distances, and also the reflective properties. I just wanted to look at all four of these together so we could see that there are some big similarities, algebraically and geometrically.